So today we have the chapters 1 through 5 no calculator section. We are starting on question 1, which is find the limit when the limit of when delta x approaches 0 of 2 to the 2 plus delta x minus 2 to the second power over delta x. So we immediately know that this part of the function, 2 squared, is the part of the function that we want to focus on. This is what we have to solve in order to find the limit. So what we can infer based off of this beginning part is that these two are similar in the sense that they share a similar exponent. So what we can do is we can see that as delta x changes, that this exponent of 2 will change over time, which means that we can simply rewrite 2 squared as 2 to the x. So now we have to write 2 to the x as something that we can take the derivative of. So we take 2 and turn it into the natural log, and so we get e to the natural log of 2, and then we have this x which remains to the power of the natural log of 2, which we can rewrite by multiplying x times the natural log of 2 as e to the x natural log of 2. So now we have to find the derivative of this to help us find the limit. So what we already know is that e to the x natural log of 2 will be in the end product, so we can write it out in front. And then we have to do the product rule on our power. So the derivative of x is 1, we get it times the natural log of 2, and then we have to add x times the derivative of the natural log of 2. The natural log of 2 is just some number, so it's 0. So we get the natural log of 2 plus 0, which turns out to be the natural log of 2. So now we can take this over here, and based off of the fact that 2 to the x was represented as 2 squared up here, we can infer that x equals 2, because 2 satisfies the relationship. So now we get the natural log of 2 times e to the 2 natural log of 2, which you can rewrite as the natural log of 2 times e to the natural log of 4, since 2 squared is 4, and that's inside of the natural log. So now we can rewrite this as the natural log of 4 times 4, since e to the natural log of some number is just that number, which turns into 4 times the natural log of 2 based off of an algebraic multiplication property, which results in the natural log of 2 to the power of 4 based off of an exponential natural logarithm rule, which turns into the natural log of 16. Alright, so for our second question, we have to find the derivative of f of theta equals 3/5 sine squared 3 theta. So for this one, it's really simple. We can rewrite this function as f of theta equals 3/5 sine in parentheses 3 theta squared. So this makes it easier to identify that we have to use the chain rule in this whole process. So what we can do is say f prime of theta equals the 3/5, we can just bring it down, times 2, because we moved the squared into the front. So we have 2 times sine of 3 theta, so we just carry the sine 3 theta down. Then we have to do the derivative of the sine 3 theta part, so we get times 3, because of the 3 theta, cosine of 3 theta, since the derivative of sine is cosine. And then once we simplify it all, we get 18 sine 3 theta cosine 3 theta over 5, since 3 times 2 times 3 is 18, and all of this is over this 5. So for question 3, we have determined the area of the given region. So one way that you can do this just by eyeballing it is drawing a rectangle around the area in which the graph is given. So since we go from 0 to 1 in terms of y and 0 to 1 in terms of x, we can calculate the area of this box as 1 unit squared, and then we can look at our choices and say, well, this looks like 2/3, so we can pick 2/3. But the actual way to do this with calculus is we have this function right here, so we can distribute the 4x into within the parentheses, so we get y equals 4x minus 4x squared. And then we take the integral of this to find the area underneath the graph. So we get 4 times the integral of x minus x squared dx, because because we can factor out a 4. So this leaves us with 4 times x squared over 2 minus x cubed over 3, which we can simplify into 2x squared minus 4x cubed over 3. And since we're going from 0 to 1 on the x, we're solving from 0 to 1. So when we plug in 1, we get 2 minus 4/3. And then when we plug in 0, 2 times 0 is 0. 4 times 0 over 3 is also 0. So you just have to worry about this part. 2 minus 4/3 is 2/3, which is how we get 2/3. Alright, so for question 4, we have find the derivative of y equals the natural log of the square root of x squared minus 12. So one thing that we automatically know is that with a square root, it's like taking what's inside of the square root and taking it to the 1/2 power. So what we can do is we can rewrite this equation as y equals 1/2 times the natural log of what was inside the square root, which is x squared minus 12. Now, to find the derivative of this, we do dy over dx equals, we take the 1/2 down. With the natural log, we know with the natural log of x, it's 1 over x. So we take this and put it underneath 1, so we have times 1 over x squared minus 12. But then in this case, since it's not just simply x, it's something else, we have to take the derivative of it as well. Not to say that when we have the natural log of x, we don't take the derivative of x and multiply it by 1 over x. It's just that we don't have to, since the derivative of x is 1, and 1 over x times 1 is 1 over x. So the derivative of x squared minus 12 is 2x, so we multiply by 2x as well. So then we get 2x, because 1 times 1 times 2x is 2x, over 2 times x squared minus 12, which is 2x squared minus 24, which we can then factor out 2 on the top and bottom. So we get x over x squared minus 12. So for question 5, we're asked to find the definite integral of x squared over x cubed plus 5. So immediately we can do one thing, which is u substitution. So we can set u equal to the denominator of this function. So we get du over dx equals 18x squared. And we can rewrite this as du over 18x squared equals dx. So this will come in handy because this can replace the dx. And then we can take this and plug in u instead, so we can rewrite this whole thing as x squared over u times du over 18x squared. So x squared divided by 18x squared is 1 over 18, so we can write that on the outside. So then on the inside of the integral, we now just have 1 over u, since this can turn into a 1, since there's nothing on top anymore, du. So when we have 1 over u, or 1 over any variable, it's just the natural log of whatever that variable represents. So in this situation, we get 1 over u, so we can write this as 1 over 18 times the natural log of u plus c. We know that u is equal to this right here, so we can substitute 6x cubed plus 5 in for u to get this answer. And we have the plus c because it is the constant of integration. Alright, so for question number 6, we have to find dy over dx if y equals x to the 7th times e to the x to the 5th. So finding dy over dx is the same as finding the derivative. So with y equals x to the 7th times e to the x to the 5th, we can immediately see a product rule occurring. So when we go to write the derivative of this, we can take the derivative of the first term, which is 7x to the 6th, multiplied by the second term, and then we tack on x to the 7th times the derivative of this part, so we get x to the 7th down here, and then the derivative of e to the x to the 5th is x to the 4th, and then we have times e to the x to the 5th. Now what we do is we simplify all the terms together, so we get 7x to the 6th, e to the x to the 5th, plus 5x to the 11th times e to the x to the 5th. And since they both share e to the x to the 5th, we can factor that out. So we get e to the x to the 5th times 7x to the 6th plus 5x to the 11th as our final solution. Alright, so for question 7, we have to find the equation of a tangent line to y equals 9 to the negative x at the point negative 1, 9. So like with the first problem, what we can do is we can use the trick of raising 9 to the, raising e to the natural log of 9, like over here. So we get y equals e to the negative x natural log of 9. We do the same thing before where we took the derivative. So we have negative 9, or negative natural log of 9, because that is the derivative of the top part, times this whole part right here. So we plug in the negative 1 for x to help us find the slope of the tangent line, which when we plug in negative 1, we get negative 9 natural log of 9, because this turns out to be e to the natural log of 9, which, again, e to the natural log of some number is just that number, so we get the 9, and then this is still negative natural log of 9, so 9 times the negative natural log of 9 is negative 9 natural log of 9. So to find the tangent line, we have y minus 9, which is the x value, the y value of the point, equals, and then we have the slope, and then in parentheses x plus 1, since in point slope form it's x minus the x value of the point, but since we have two negatives it becomes a positive. Then we add over the 9, so we get y equals negative 9 natural log of 9, x plus 1 plus 9. And then we can factor out a negative 9 from this whole thing, so that we get y equals negative 9, in parentheses 1 minus the natural log of 9, because this becomes 1, negative natural log, negative 1 natural log of 9. You can flip the signs, and then you get the x plus 1 down here in parentheses.
Go.
Alright, so for question 7, we have another...
Question 8.
Question 8. We have another derivative problem, except this time it features arc sine. So we know with arc sine that we have 1 over the square root of 1 minus the function inside of the sine function. So in this situation we have a 7, so we can just bring it down over here. And then that property that I just mentioned, we apply it here. So it's the 7 times 1 over the square root. We have the 1 minus, and then inside of the sine function we have x minus 1. So we can plug that in here, and then that's squared. So what happens is we simplify this to one whole chunk. So we have 7 over the square root of 1 minus x squared minus 2x plus 1. So that's after we FOIL x minus 1 squared. And then we have 7 over the square root, and then we apply the negative to all the terms inside the parentheses in this next step, which we can then simplify to 7 over the square root of negative x squared plus 2x, since the only things that get eliminated are the positive 1 and the negative 1, which then, because of addition properties, we can rewrite as 7 over the square root of 2x minus x squared. Okay, so to quickly explain question number 9, we have a person in a plane. The plane is 7 miles above the ground, and the plane is flying at 300 miles per hour toward the person. So in this situation, we're trying to figure out how much the angle here is changing by as the plane is flying toward the person. So what we're trying to find is d theta over dt when x equals 3, since x equals 3 is the x value we're given in the problem. And since the plane is approaching the person, we know that since it's moving at 300 miles per hour, this means that x is going to be shrinking since it's going toward the person, which causes this to be negative. So we're going to start with a trig function to set up the d theta over dt. So I'll pick tangent in this situation because we have opposite and adjacent, there we go. So tangent of theta equals 7 over x. So when we do the derivative of this, we have secant squared theta d theta over dt, and then the derivative of 7 over x is negative 7 over x squared, and then we have the dx over dt because we took the derivative. So now we can quickly simplify this side to just secant of theta squared in parentheses times d theta over dt. And in this step right here, I just plugged in both negative 300 and 3 to get 700 over 3, so I skipped a step there. Here, we now have the square root of 58 over 3 squared d theta over dt equals 700 over 3. So we get the square root of 58 over 3 in this situation because right now we're just looking at secant, we're not looking at secant squared because the squared is being applied on the secant, so we can just find the ratio when it's only secant. So here we have 3 squared plus 7 squared equals, and then we'll call the hypotenuse h squared. 3 squared is 9 plus 7 squared, which is 49, so we get 9 plus 49 is 58. And since we're trying to find the length of the hypotenuse, we say h squared is equal to 58, which means that h is equal to the square root of 58. So this is the square root of 58. So when we do the secant, we get the square root of 58 over 3 because x is 3. So then what we do is we get d theta over dt on one side of the equation, so that way we can solve for it. So in this case, when we end up getting d theta over dt on its own by moving this over here, we get 6300 over 174 equals d theta over dt. And when you do the math, this evens out to around 36.207 radians per hour, which is the correct answer choice. And one way to tell that it's positive immediately is since the plane is getting closer, the angle is getting bigger, which means that the angle wouldn't be shrinking, therefore the rate at which the angle changes should not be a negative number. For the FRQ on part A, we're asked to identify any points of inflection, if there are any, and to justify our answer. So in this box right here, we have the important information for all 3 parts of the FRQ. And so for part A, we just have to focus on the graph of f prime. So there are 2 points where the graph of f prime touches the x-axis. It's where there are the 2 x-intercepts, which are negative 2, where x equals negative 2, and where x equals 3 natural log of 5/3, which is an ugly fraction. Now, what we can tell, based off of the graph of f prime, is that there's only one point of inflection, and it occurs at x equals negative 2. So the reason that a point of inflection does not occur at 3 natural log of 5/3 is because the graph of f prime, its slope is constantly negative as it passes through the x-intercept, meaning that f double prime is constantly negative from 0 onward, meaning that there is no change in concavity and that the function is always concave down. However, at x equals negative 2, since prior to x equals negative 2, the function has a negative slope, and after x equals negative 2, it has a positive slope. This indicates a change in concavity. So as stated over here, f has a point of inflection at x equals negative 2. Since the slope of f prime is negative prior to x equals negative 2, and it's positive after x equals negative 2, there is a point of inflection at x equals negative 2. So this means that f double prime is negative before x equals negative 2 and positive after x equals negative 2, indicating a change in concavity at x equals negative 2, because when f double prime is negative, the function is concave down, and when it's positive, it's concave up, meaning that concavities will flip, and we have a point of inflection. So part B of the FRQ asks us to find the value of f of negative 4 and f of 4. So I'll start with f of negative 4, which is the work on the bottom. So what we know is that this graph is the graph of f prime. So if we take the integral of f prime, we can get f. Now from 0 to 4, we do have an equation, so that's lucky for us in terms of solving f of 4, but it's not lucky when we're trying to solve f of negative 4, so we're going to use displacement for f of negative 4. But with f of 4, we can take the integral of 5e to the negative x over 3 minus 3 dx and split it into two different integrals, one with 5e to the negative x over 3 dx, and then one with just the integral of 3. So off to the side I have the negative integral of 3 dx is equal to negative 3x, which will be included in two steps. In this step here, we've substituted u in for negative x over 3, and we have a negative 3 du because when you allow u to equal negative x over 3, du over dx is equal to negative 1/3, meaning negative 3 du is equal to dx. So we end up getting negative 15 on the outside, and then on the inside of the integral we have e to the u du. So we can plug negative x over 3 back into u. So we get the negative 15 that we took outside. We have e to the negative x over 3, which was once our e to the u inside the integral. And then we have this minus 3x from up here when we integrated separately the 3. And then we have a plus c because we have a constant of integration. So before we can figure out what f of 4 is, we have to find out what the constant is. So we know that f of 0 equals 5. So if we plug in 0 for all of our x values and then have it equal to 5, we can find our c. So we get negative 15 times 1 because e to the 0 power is 1. And then we have minus 0 because negative 3 times 0 is 0, plus c because we don't have anything to represent c yet, and then this all equals 5. So when we simplify this whole thing down, we get negative 15 plus c equals 5, so we can just add 15 to both sides, so c equals 20. Now what we can do is we can plug the c, which is equal to 20, in to this equation, so we can move over here. We're trying to find f of 4. So since x equals 4 in this scenario, we'll plug in 4 for x instead, and c will be equal to 20. So we get negative 15 times e to the negative 4 over 3, since we plugged in 4 for this x, minus 12, since we also have to plug in 4 for this x, plus 20. And when we simplify that down, we get negative 15 times e to the negative 4/3 plus 8. Now, as for f of negative 4, one thing that we do know is that f of 0 is equal to f of negative 4 plus displacement. So what I mean by displacement is the integral from negative 4 to 0 of f prime. So the way we can find this is, even though we don't have an equation, we can use geometry to help us find the region under the semicircle. So we know that we can create a rectangle here. So if the rectangle is 2 units tall and 4 units across, we know that that's 8 units squared. So we have our 8 units over here. And then we need to find the area of this semicircle, which is pi r squared over 2, since it's half of a circle. So when we plug in the radius of 2 into the equation, we get 4 pi over 2, or just 2 pi. And since we have to find the region underneath the semicircle, we subtract that area from the area of the rectangle. So now that we have 8 minus 2 pi is our quote-unquote displacement, we can plug that in for the displacement, and we can plug in 5 for f of 0. So now we got f of negative 4 plus 8 minus 2 pi equals 5. So we can just shift 8 minus 2 pi to the other side, and we get f of negative 4 equals 2 pi minus 3. And if you want to go even further with that, you can approximate f of negative 4 to be 3.28 if you assume pi is 3.14. So for the last part of the FRQ, we are asked where f has an absolute maximum. So we already have points and their values based off of previous problems and things we were given. So we know that f of 4 equals negative 15 over e to the 4/3 plus 8. We know that f of negative 4 is 2 pi minus 3. We know that f of 0 is equal to 5. But we also need to check where x is equal to negative 2 and where x is equal to 3 natural log of 5/3. So to check for x equals negative 2, or x equals negative 2, we have to do f of negative 2. So to find this, we can use the same method we used for f of negative 4, where f of negative 2 plus some displacement is equal to 5, since going from here to here requires some movement on the graph, and we know that when f is 0, f is 5, or when f of 0 occurs, the graph is at 5. So we can do f of negative 2 plus 4 minus pi equals 5. So we get the 4 because the box that we have to calculate the area within is 2 this way and 2 up. So that's where we get our 4 from. And then we have a quarter circle now. So the area of this region is pi r squared over 4. Since the radius again is 2, we get 4 pi over 4, which is pi. So we have to subtract that pi from this region. So that's how we end up getting f of negative 2 is equal to 1 plus pi. And this makes sense numerically, that f of negative 2 is greater than f of negative 4, since the slope is increasing after x equals negative 2. And also since when f of negative 4 occurs on the graph of f prime, the slope is decreasing. So now that we figured out that f of negative 4 is less than f of negative 2 is less than f of 0, we just have to worry about 3 natural log of 5/3 and f of 4. Now, based off of the graph, we know where the max occurs between those two. It occurs at x equals 3 natural log of 5/3. So the reason that this occurs is because the graph of f prime is positive up until it hits the x-intercept 3 natural log of 5/3. Once it passes 3 natural log of 5/3, the graph starts decreasing, meaning that f and its values will become smaller, meaning that f of 4 must be smaller than f of 3 natural log of 5/3. So this means that f has an absolute max at at x equals 3 natural log of 5/3, because since 2 pi minus 3, which is f of 4, is less than 1 plus pi, which is f of negative 2, is less than 5, which is f of 0, and f is increasing from 0 to 3 natural log of 5/3, meaning that f's values are going to continue to increase. We know that 3 natural log of 5/3 is the absolute max. We also know that because after 3 natural log of 5/3, the graph is decreasing, meaning that f's values will get smaller after 3 natural log of 5/3, meaning that that is precisely where f has an absolute max.